Okay, we're going to go ahead and get started with our next presenter. Mary Windsor wasn't able to be here today, so we have Howin Chu, also from the Iowa Flood Center instead. And let's give him welcome.
Thank you, guys. Good morning, everybody. Thanks for coming to my presentation. My name is Howin. I'm a research assistant at IIHR Hydroscience. My topic today is going to be an Iowa prototype for generic watershed decision support system. Basically, I'm going to present a web-based system for watershed and hazard management. So here's our team. The principal investigators are my advisors, Professor Marian Musty and Professor Ibrahim Demir. Both of them are from Iowa Flood Center. Myself, in the project, I'm a system architect. I designed the architecture and the framework. And I do work with two colleagues, Haider Hamid, a software engineer, and Mary Windsor, who's a GIS expert. To get started, I'll go through my outline first. For this presentation, I'm going to talk about the objective and a brief introduction on the project, what's this project for, who funded the project. Then I'm going to present some key features. Our system can be broken into watershed resource information and watershed planning, and I'll give a live demo, not really live demo, but more like a screen recording. I can give a live demo depending on the quality of the internet. And after that, I'll talk about the implementation, basically technical details, how we built this web product. It's a cyber infrastructure. In the end, I'm going to talk about the vision for future development. So first, I'm going to talk about the objectives. This is a project funded by the U.S. Army Corps Institute for Water Resources, aimed to achieve following goals, and it is an operational system. It has been applied in the past multi-hazard tournament hosted in Cedar Rapids last September. And the goal include inform watershed stakeholder on the current status and immediate future of Iowa watershed, as well as integrating watershed data resources from real-time sensor past modeling results in one place from heterogeneous sources, and also the platform will uniformize the data format, the data standard, and the metadata standard, prepare those data for further data-driven and model-driven analysis. So as a web platform, the system also facilitates communication and data sharing as well between communities. As we all know, watershed management is an integrated task. The integrated watershed management concept was proposed in the 70s, and it faces a lot of challenges. Like it requires multi-roles, multi-players, collaboration between stakeholders, between planners, between government agencies and researchers, and the system provide an easy way to share data, to facilitate communication, and also in this platform, it establish competitive gaming environments, as I will present later. Then in the last, the system provide a generic platform for generic watershed management task, and also for decision support in hazard management processes. So as many other web applications, we do have a cover page. Should I? So in our cover, yep. So we have a short paragraph. It's a screen recording. Talk about our platform, and we have an interactive map on the right-hand side. Basically, it's a map of Watershed Management Authorities. When we built this platform, there were only 9. Now there are 13. It's interactive. We have 4 main functional tabs. The first tab will launch the main decision support system, our main platform. I'll talk about later. We do have some child system. This one is about our watershed infrastructure, culverts, dam, reservoir, for management and for maintenance, for inspection, and we do have water quality parameters here too. And the last tab is about community and collaboration. As I mentioned earlier, the watershed management is a joint task. It requires collaboration. This page will guide the user to different homepage of different agencies and watershed communities. So we also have an about page providing a detailed introduction on our project. Our project also traces back to the Iowa watershed approaches from the IIHR and the Flood Center. We also have a support page providing technical support, talking about the browser compatibility. Also, we have some online tutorials as well. The contact page will point back to our pinpoint location of our institute and also some contact information. So now let's go through some key features of our web-based system. So as I mentioned earlier, our system can be broken down into watershed resource information system and watershed planning. So a watershed resource information system provides generic information about watershed introduction and watershed attributes. So they have two sections. The first section is a watershed search engine. It's the first step in the workflow. Basically, it's a search engine enable user to define the study area based on point of interest. And then after the study, the study area is defined, the system will aggregate all the data resources and prepare an overview page. Then I'll talk about the planning later. We adopt a 7 steps planning, and I'll list a step. So the first demo I'm going to go through is about the watershed search. So we'll launch the main system first. Then actually you can say it's the first workflow in the platform. They do provide different search criteria. They are criteria for defining point of interest. We can view all the data at the state level, at HUC 8, HUC 12 level, and also at the county and city and place of interest level. So it's a search engine. Actually, when you hover on, it will show you the watershed name, HUC 8 name, and also HUC ID, the HUC code. And it's autocomplete. You can search watershed by name. So basically, it treats the upstream drainage area of a selected HUC 8, and also it treats the downstream effluents, as you can see. Here's a HUC 12. It's much denser than HUC 8. You can just simply click on map to select the watershed you want to create a plan or you're interested in. You can also search by the HUC code, and it's autocomplete again. So basically, it will match all the watersheds that based on the user input. We do provide a search criteria based on county, so it's also for the public participants and also engagements, basically educating people where the water comes from. If somebody is living in the Johnson County and he wants to know like the upstream drainage area, he can use this tool. And now I'm selecting the City Rapids. Basically, it's tracing upstream drainage area based on the city location. And we can do some geocoding and also randomly click on map to trace the watershed. All the watershed search engines are developed based on the NHD Plus version 2. We use topology there, and we did some algorithm basically to make it more effective and faster too. This criteria is about project-based watersheds. So in Iowa, we do have a lot of watersheds has a specific projects, and there are specific models running in this watershed. We only enable the Middle Cedar Basin for these projects. We do have another version of a system. We have 10 watersheds with different models, and each one of them have an interactive interface for the user to play with, to visualize the modeling results, to get an idea about the study. And I'm going to use the Middle Cedar Basin, which is basically the study area of the U.S. Army Corps multi-hazard tournament last year, to demo the rest of the features. So after a study area is defined, we're going to talk about the data resources in watershed. Now, as you can see, we have an overview page talking about the population. Everything is dynamic about the area of the watershed, also sub-watershed within the study area. It's a real-time generated, and we do have a data inventory. Those are all the real-time sensors, the parameter measured by the sensors and connected to their pertaining agencies. And here are the past models. Like I mentioned earlier, there are sub-watershed within the study region, and those watershed has models, and I'll give a demo. So here's the Indian Creek watershed, basically to launch a separate page, separate problem-solving environment. That's the boundary of the Indian Creek. It's a model run by the U.S. Army Corps. It's a Geisha model, part of the FSA pilot project, basically exploring the effect of CRP in flood peak reduction and flood damage reductions. It's a very interactive user interface with a visualization. User can choose different scenario, different land use, and visualize the effect on map. Those applications can be extended to many models, and it's for public education purposes and also for scientific communication purposes as well. So other than the previous model visualization, we also have real-time sensors. We connect EPA sensors, USGS sensors, and Iowa flood center sensors too. They have different data domains, including hydrology, hydrometeorology, hydromorphology, socioeconomics. And I'll give a demo. So everything is real time through the web services. It's an Iowa flood center sensor, stage sensor. We have a metadata page. Then we can launch a time series. It's very similar to the IFAS, actually. We have a location of the sensor, we plot time series, and we have some statistical information shown in the box plot. And in our system, we can compare measurements between different sensors with the same parameters. So now I'm plotting two measurements from two sensors in the same graph. And now I'm switching to the discharge. So that's the end of the first components, basically presenting watershed data resources to the user. Now we're going to the watershed planning components here. Like I mentioned earlier, we adopt 7 steps planning processes. It was firstly adopted by the USDA and the EPA to synthesize the past planning documents. Go through from the objectives in which we define what the plan is for, some metadata for the plan. Then we collect the data resources in the study area. Then we select alternatives, basically the management practices for specific watershed management task. Then we go through the assessment, selection, implementation, and evaluation, which is a post-construction evaluation, if we have any watershed management practices. So here is the demo how we create a plan in our system. So we have like I mentioned earlier, we have a progress bar with the 7 steps, and we have a previous plan. Those are the past tournament plan. As you can see here, that's the actual tournament hosted in Cedar Rapids. We have planners, participants, and also referees from the U.S. Army Corps who are trained professionals as judges to evaluate user performance. And then now we're going to create a new plan. So we're going to fill in the name of the plan, the objective, and the type of the plan. By default, it's a multi-objective, but it's based on the user's interest. So those are some description and the metadata for the plan. Also the timelines, other descriptions, then we'll finish creating a plan. So now the new plan is created, the system will move to the second step, basically the resources, and the resources I have already presented in the previous components. It's basically the same thing, integrating past models and sensors, real-time sensors. So I'm going to skip that part and go directly to the alternatives. So as I mentioned earlier, our system is a data and model-driven platform, and in order to assess the alternatives, we have 8 simulation models, multi-domain, range from physical models to socioeconomic models, basically HACRAS, HACHMS, HACFIA, and we run those models within the Middle Cedar Basin. Actually, the U.S. Army Corps runs the models. And we build the workflow and the schema. We connect different components, and those models are run under 4 climate scenarios. In our system, those scenarios will be labeled as terms, and each term is representing historical, flood, drought, or climate change. And we provide 40 multi-hazard practices. They are alternatives, and I'll show later. So this is our interface. As you can see here, we have a panel offer all the alternatives the user can select. We have a localized actions and a watershed actions. Then there's a small functional bar providing the constraints. You can see from here we have turn 1, and we also have a budget limitation, and we do have a map component. Here's the demo again. So after we finish the step 1 and step 2, we go to the step 3. So the localized actions include raise the well intakes, relocate structure, elevate structure, and also place levees. And the watershed actions include change land covers, like putting riparian buffers. And now I'm making some random selection just to demo the performance of the systems. So as the user selects actions, the budget will goes down based on the price, the cost of each management practices. So after the turn 1, we'll proceed to turn 2, and after each turn, the system will provide an evaluation, basically scoring, to assess the user's performance. And we have a 2 kind of scoring system, and I'll present later after we finish all the turns. So from turn 1 to turn 3, the budget is a fixed amount of money. So basically, if we use up all the budgets, we cannot do anything, and we cannot revert our practices we have installed. And now I'm over budget, so it becomes a deficit. That's why the text shows in red. Now I'm proceeding to the turn 3, and those are the evaluation for each turn. So in turn 4, it's a climate change turn at a different scenario. So everything is resetted. We can basically reset all the past implemented alternatives we have selected in the previous 3 terms, and also we get more budgets, more money, more funding for those practices. In the end, we also get a scoring for our performance. The technical scores are from the model simulations. As I showed earlier, we have 8 models, and which will evaluate the performance of a user selection. The jury scores are the score rated by the referees. They are professionals from the U.S. Army Corps. So that's the end of planning processes, and actually it's a web-based system. During the tournaments, we have a user login feature. Now it's disconnected, but basically each user's performance is tied to their login accounts, and we have an administration system that can evaluate different planners' performance and their approaches to mitigate like a hazard, flood or drought. In this session, I'll talk about the implementation. So I'll start with the data structure. As I mentioned earlier, our watershed infrastructure is built on the top of an NHD Plus framework. Basically, we have a physical boundary of stream segments and also different watershed boundaries. The NHD also carry topology between rivers. That's why we can trace the upstream watershed and downstream watershed. We did some improvements. We generate the topology between different levels of watershed too to improve the speed. And for the real-time measurements, we use a quasi-ODM. It's a good data model. It's a relational data schema to store the time series data. We use a relational database, and we use a schema in it. In terms of technology, we use AngularJS in the front end. It's a JavaScript MVC. It's very good for the single-page application. And the GeoServer is a map server for providing web map services, spatial components, web feature services. And those are some common front-end technologies: HTML, CSS, JavaScript. Leaflet is our main mapping engine. It's also a JavaScript, interactive JavaScript map engine like Google API and OpenLayers. For all the geoprocessing services, we use QGIS, and for our spatial database, we choose Postgres. Basically, PostGIS is a spatial extension of a Postgres database, and all the technologies are open source. This is our architecture, and we choose a 3-tier architecture, including presentation tier, logic tier, and the data tier. It's very common in these days web developments. In the end, I'm going to talk about the future work. As I mentioned, our system is built on the top of NHD+, so it's extendable to national level, and the U.S. Army Corps, they are planning to organize a new multi-hazard tournament in Texas. The new tournaments will have 2 watersheds, 6 damage center, and 2 scenarios. And we are going to implement a new system, basically extend our current system into Texas this summer. That should be end of my presentation. Thank you. Are there any questions?
Got about 7 minutes left before lunch break. So
it's a good timing.
Good time, yeah.
Oh, please.
I've just been noticing you have a fairly robust system, and you said with the front-end user, as far as requirements, is it JavaScript and then just a regular internet browser, or do you need anything else as far as?
There are so many ways to develop such kind of system, but for the interactive decision support or information system, we prefer to use a single page web application, basically SPA, so the user can go through a lot of workflows without reloading the page. That's why our system specifically is heavy on the front end, and we do use a lot of JavaScript.
I'm
And-
involved with the development of the system here at Iowa State, and right now we're going to be setting that up in the cloud. Is your system just a server there at U of I, or do you have a cloud-based system in the works too?
We do have a backend, and these days, like many people use a service-oriented system. So basically, the query data, the query modeling results, we retrieve different resources from web services. So we can move all the modeling processes into like a cloud or a distributed system, and through web services, the front end, the JavaScript parts will get data and visualize it and produce an interactive interface for user to play with.
Thank you.
Thanks.
So I was at the tournament in September, the Hydro tournament. It was very informative and interactive. It was a lot of fun.
Thank you.
I wondered, is this usable right now for any other watershed besides the Cedar watershed? And also, my other question is, what is needed to make it useful so you can use it in other watersheds?
So basically, we developed this this platform based on a framework. So the framework is more like a data and model-driven framework. So if you have if you have a simulation data for other watershed, we can definitely make it work very easy.
Is there data for other watersheds that you know of right now?
We do have some like other web application, not really at a tournament level, but for specific purposes. For example, the Iowa watershed approach, we do have some simulation modeling results from the HyHMS models, and we have another child application developed for the Iowa DOT for covert inspection and management. Basically, we have a Russell, and we have some multi-criteria decision analysis behind. So it's basically it's model and data driven, and it can be extended to any watershed.
You went through the tournament, but you could show a lot of other stuff.
Yeah.
What other watersheds are those? Do you know?
We have a Turkey River watershed. We have a Soap Creek, South Sequest. But now the IIHR, like my institute, is hosting another web applications called IWA, I think, for the integrated watershed management and Iowa watershed approach. And our platform serves as a prototype.
So are all of these modeling runs done on demand, or are they done ahead of time in mass and then stored in a database, and then the interface goes and fetches the results?
Actually, we can do both these days.
Cool.
So basically, if it's a previous modeling results or it's a historical modeling results, then we fetch it from the database. We can run real-time models, and the Iowa Flood Center has a cluster. They do, for the IFLS, they do run some climate modeling or water temperature modeling on fly.
Cool. More questions? All right, let's give Colin another.
Thank you for coming.
And you got a